Welcome to 2D kinematics, acceleration in 2 dimensions. So we've been working on projectile motion and talking mostly about velocity, and now we're going to jump back into acceleration problems. And so so let's determine which scenarios involve acceleration. Let's go through these. You are skating forward at an increasing speed. So here, note that your speed is increasing, okay? That means the speed is changing. Anytime your speed is changing, then it's an acceleration problem. Okay, so this is correct. This is an acceleration problem. A bird is taking off into flight raising higher and going faster in the air. Okay, so now this one, the bird is going higher and it's also going faster. So yes, that would be an acceleration problem. A cyclist slows to a stop. Is his speed changing? Yes, his speed is changing, so therefore acceleration. And a transport truck maintains a constant speed while turning. So notice here, it's a constant speed. So that would mean that it's not acceleration, however, it's turning. Now, when you're talking about acceleration, remember acceleration is a vector. And so since it's a vector has a magnitude and a direction, okay? And so both of these would have to stay constant in order for there to be no acceleration. So if the direction is changing, if this is staying the same, but this is changing, there's still acceleration. And one way you can think about this is if you're in a car, when you don't feel any force on your body, like imagine if you're at a stop sign or a stop light, and then imagine that that the gas pedal is pushed really, really hard when the light turns green. Your body's going to be pulled backwards. That your body's experiencing an acceleration. If you're going 120 miles per hour at a constant speed, your body doesn't feel any forces on it. But if you're like going from 0 to 120 miles per hour, your body feels that force and it's being pulled back because of the acceleration. Now, if you're going 120 miles per hour and all of a sudden you slam on the brakes, then your body's going to be jolted forward because of the deceleration. The speed is changing and your body feels that. Now think about if you're going around a curve in a car really quickly at a constant speed. Let's say you're going around a sharp, curve at 50 miles per hour at a constant 50 miles per hour. Well, your body is pulled to the side. And your body is pulled to the side because it's expecting to go in one direction. As you change direction, it keeps being pulled in that direction. So in order for acceleration to take place, either the magnitude or the direction has to change. Okay. So either the magnitude or the direction, or both. Recall that acceleration is defined as a rate of change in velocity, which is a vector. The result of this definition is acceleration occurs when an object's direction of travel changes. Examining the equation for acceleration. So we have acceleration is equal to v2 minus v1 over delta t. We could solve for a non-collinear acceleration, also called acceleration in 2 dimensions, by subtracting vectors v2 minus v1. Thus far, we have only added vectors. How can vectors be subtracted? Okay, so we did vector addition, right? But how do we do vector subtraction? So one way to look at this is you can look at the equation 5 minus 2 equals 3. But you can also make that equation say, this is the same equation right underneath it, which is 5 plus negative 2, right? So 5 minus 2 is the same thing as 5 plus negative 2. So in order to subtract a vector, what we do is we apply the same reasoning. We add 2 vectors. But what we do is we take the second, the negative vector, if you will. So in this case, this one. And you make it a negative vector. So, for example, here we have 5 meters north minus 2 meters west. So if we look at our directions, here's north here's south, here's east, and here's west. So when you're subtracting 2 meters west, or I think an easier example to start off with is if we had 5 meters north minus 2 meters south, okay? We could look at this as 5 meters north plus, and here we're gonna change this sign. It's gonna be plus negative 2 meters south, right? Well, what's negative 2 meters south? Well, if we flip the direction, it would be 5 meters north. And then if we flip this direction, it would be plus 2 meters north. So then we would end up with 7 meters north, okay? But here's a different example. We have 5 meters north down here, minus 2 meters west. So 5 meters north plus negative 2 meters west, or 5 meters north plus 2 meters east, okay? To find the negative of a vector, keep the magnitude the same and reverse the direction. If we were to look at this in terms of like vectors and we just drew them out, if we had, let's say this is vector A, and we can say this is vector B. What would negative vector B be? If we wanted to do, if we said A minus B, that's going to be the same thing as A plus negative B, right? Well, what's negative B? Let's change our color. Negative B is going to be the same thing, so we can actually just copy this, right, and duplicate it. But then we'll have to erase this. Oopsie, that didn't work. So I'll just draw it. It's going to be the same size and the same angle, but instead of having the arrow on this side, it would be on this side. So this would be negative B vector. Okay. So then when you did vector addition, you would put this on to here, and your resultant vector would be starting here and ending here. Okay. Subtracting vectors. To check, you can sketch each vector. If you found the negative version of the initial vector, when you add them together, the resultant must be 0. So if we go back to our example with our vector, so like here, if this is, I'll try to draw it nice and neat. If this is vector B, and this is negative vector B, when we add these together, if we were to start here, right, and then we add this vector onto the other one, so we put the tail of this one onto the head of the other guy, where do we end up? Well, we end up in the same place we started, so therefore it's 0. Okay, so try these. We have acceleration of 4.2 meters per second north. Very good. Here we have, now we're supposed to do negative, it's just showing that 4.2 meters per second north, and this is an acceleration, so they made a mistake here on this slide. This should be squared, right? And this should be squared, because acceleration is our change in velocity over our change in time, right? And velocity is meters per second over seconds. So the units for acceleration is meters per second squared. So let's fix all that. So squared. But what this slide is trying to show you is that 4.2 meters per second squared south is the negative of that. Okay. Okay, 1.25 kilometers per hour. So this is the velocity. If you want to make it a acceleration, the units would have to be hours squared. Okay, so southwest, here we go. And if we wanted to do negative b would be 1.52 kilometers per hour northeast. It would be going the opposite direction, right? So what they did here and with the negative is they started here and drew it this way. Okay, here we have 76 meters per second. North, 25 degrees west. And then the negative version of that, it's going like this, starting here and ending here. Here's another one. Pause the video and try this yourself. And then again, the negative starts here and ends here. And here's another one. I'm going to speed through some of these. You can pause the video and try to do these on your own, but you get the idea, I believe. Okay, what relationship between the directions of the two vectors, positive and negative, did you notice in the examples above? So the value of the angle stays the same. Each direction is flipped. So north goes to south, east goes to west when you're doing the negative version. To find the acceleration in 2 dimensions, ensure all units match. Meters per second and seconds in most cases. Write out the known values, v2, v1, and delta t. Determine negative v1 by changing the direction of v1. Draw the vector addition, v2 plus negative v1, to determine the magnitude and direction. Because remember, basically they're saying, how would you solve this problem? Is you would have to make this into v2 plus negative v1 over delta t to determine the magnitude and direction of the difference in velocity. To find the, okay, and then here we continue. You divide this delta v, and remember that delta v right here is equal to v2 minus v1 to determine the average acceleration, which has the same direction as delta v. So remember, this is giving us our average acceleration. So if you have a constant acceleration, this will give you, but let's say you're driving and you're speeding up and slowing down and speeding up and slowing down. It's not going to give you instant, it's only going to give you the acceleration over this time period, the average acceleration over that time period. So if your acceleration is changing, it just gives you the average. If it's staying the same, then your instantaneous and your average would be your instantaneous if you're not changing your acceleration. Okay, let's give an example. You maintain a constant speed of 85 kilometers per hour as you use the on-ramp to enter the highway. Your direction changes from north to east in the span of 2.1 seconds. Determine the average acceleration over that time in meters per second squared. Okay, so here we're going to turn, we know that the magnitude of V2 is 85 kilometers per hour. And we know that the magnitude of V1 is 85 kilometers per hour. Okay, so the magnitude, and actually here, I should remove that because we didn't show the direction. We're just talking about the magnitude. So here we can convert that. And we get that the magnitude is 23.61 meters per second. So now we write down the values. We have 23.61 meters per second north and 23.61 meters per second east. And our delta t is 2.1 seconds. Okay, so our negative V1, because remember, we are doing acceleration, is V2 plus negative V1 over delta t. So our negative V1 right here is going to be the same magnitude, but the opposite direction. So it's south. Okay. So we're going to draw our diagram. We start by doing V2 is 23.61 meters per second east. So here's our V2. It's east. And then we're going to add plus, that was our V2, our negative V1. Our negative V1 is 23.61 meters per second south. So here, this is our negative V1 is 3.61 meters per second south. So our resultant vector starts here and ends here. Is going to be this. That's our delta V. And how can we solve for this? Well, this is a right triangle. We could do Pythagorean theorem, right? So 23.61 squared, take this, square it, take this, square it, and then you take the square root of both sides, and you're going to get the magnitude of the delta V is going to be 33.39 meters per second. Okay, so this will be 33.39 meters per second. Now, what's the direction? Well, because this is these are both the same size, I know just intuitively that this is going to be 45 degrees and this is going to be 45 degrees because we know that it's an isosceles triangle, and since these are the same, these angles have to be the same. So I know that if I look at that, the angle is going to be southeast, okay? And it's going to be 45 degrees, okay? Now to solve for acceleration, we have now we can take our delta V that we just found over delta T. So our delta V is 33.39 meters per second southeast over 2.1 seconds. And the resultant is we take that divided by that, we get 15.9 meters per second squared southeast. Therefore, the average acceleration of the vehicle is basically 16 meters per second squared southeast. When the directions involved are more complicated, we rely on angle rules. Recall the angle rules. So just some geometry review right here. If you have two parallel lines, here's one parallel line, and here's another parallel line, and you draw a line through it, the opposite interior angles, this one and this, are going to be equal. Okay. Also, if you have a right angle, the complementary angles here, alpha and beta, those add up to be 90 degrees. And here, if you have a straight line, all the angles add up to be 180. Okay, example 2. A dancer changes velocity from 3.1 meters per second, east 20 degrees north, to 4.8 meters per second. Okay, determine the average acceleration that occurs over 1.1 seconds. I'll check that the units match. Do the units match? Yep. Write the known values. So here we have the known values. V1, V2, and delta T. And what are we solving for? We're solving for acceleration, right? If we go back to here, usually when I list out things, I also list out what I'm trying to find. So here I would just list that. So since we were trying to find acceleration, and acceleration is our V2 minus V1, or we can say that's the same thing as plus negative V1 over delta T. So our negative V1 is going to be 3.1 meters per second, but we change the east to west and the north to south. So we can draw this out, right? We have the V2, we start with V2 because here we start with V2. So we have 4.8 meters per second south, 18 degrees west. Okay, so here's our V2. Say I want to use my highlighter. Start with our V2, and then we're going to add 4.8 meters per second south, 18 degrees west. Excuse me, we're going to add, this right here. 3.1 west, 20 degrees south. So here, this is 3.1 west, 20 degrees south. We started right here, we're ending here. So here is our resultant vector right here. Okay. Now, this is a little bit trickier, right? It's not quite as easy, but here we have, if you look at geometry, we have our angles. Let's choose a different color. Let's use blue. Here's our alpha. And this right here is 22 degrees here. We know that this over here is 18 degrees. And we know, so like here, this is getting a little bit messy, but if you look at, if we make a coordinate plane here, right, we can extend that and you can see that this line and this line are parallel, right? So we know that this angle here is going to be the same as this angle here because this is alternate interior angles. So if this right here is 18 degrees, then this over here will be 18 degrees, okay? We know that this here is 90 degrees, right? And we know that this is 22 degrees. So now we know that this angle, theta, is 22 plus 90 plus 18. Okay. Trying to see if there's anything else we know. I think that's all that's shown there. Okay. So we know that this is 130. Okay, so now we would use the law of cosines to solve for V2. So here we have the law of cosines. Because this is what we're solving for, we plug everything in and we solve and we find that the delta V, because this is delta V right here, is 7.196 meters per second. Okay. Now here, I think they're just showing an alternate way. Oh no, now we're finding the angles, okay? So now we have sine of alpha over 3.1, because this is 3.1, right? Because remember law of sines, it's the sine of the angle over the opposite side, okay? And that's going to equal sine of theta right here over delta V. And so we know what this is. We plug that in, and we can solve for sine of alpha. We can solve that alpha equals 19.3, okay? And so here, this angle here, this total angle here, is our 18 degrees plus our alpha. So 18 degrees plus 19.3, see, would give you this angle, which is 37.3. So we have our magnitude 7.196, south 37.3 degrees west. Okay, so now we have that. So now that we have our delta V, we can solve for our acceleration. Now this is a little bit easier because we have our delta V and our delta T is 1.1. So we just multiply that out and we get this. Okay, these are a little bit complex and two-dimension. One-dimensional problems are much simpler. If you had a similar problem where you had, if we went back here and we said, and instead of it, if it was just 3.1 meters per second north, and this is 4.8 meters per second north, if they were both going the same direction, then our acceleration would be our change in velocity over time, which would be V2 minus V1 over delta T, right? If this is our V1 and this is our V2, then our V2 is 4.8 meters per second north, right? Minus 3.1 meters per second north, or you could say plus 3.1 meters per second south over 1.1. And so this would just be 4.8 minus 3.1 divided by 1.1. So it's a lot simpler when it's in one dimensions. The two dimensions make it much more complex, but I want you to understand this, how simple it could be with just one dimension. Okay? Any questions?